everybody. All right, so we have talked about how to calculate Q, how to calculate the amount of energy that is released or absorbed, which is Q. And we've also talked about the heat of vaporization and the heat of fusion when things go through phase changes. So when something starts as a solid and moves to a liquid, or vice versa. Well, today we're going to talk about heat exchange, right? Because we know that things transfer energy everywhere throughout our universe. So what heat exchange is that energy in is equal to the energy out. So let's dive into that a little bit more. So one example I like to use to kind of describe this situation is if you've ever played pool, you take the stick, right, cue, and you strike the cue ball. And if you strike the cue ball into that triangle of the billiard balls, of the pool balls, all of the energy that you transfer from the pool stick to the cue ball ultimately is transferred into the pool balls themselves. And we can see here's kind of the cue ball, and it's going to cause these balls to go every which way. It's going to cause all of these balls to move in all different directions. So the amount of energy that was here hit these balls and caused them to move. So the energy was transferred from this one ball into many. Now, the speed at which this one was moving might not necessarily be the speed at which all of them are moving, but the energy that came from this cue ball is then transferred to all of these, and they will move out in whichever direction they choose because of, I wouldn't say choose, but because of the way that they hit all the other balls that were in this area. So energy was transferred from one object to many. So we can kind of visualize this a little bit more with particles. So we already know that when particles are moving slower, it's typically because they're colder. So if there's low movement of particles, they're typically at a lower temperature. Whereas when things are hot, they're moving a lot faster. Well, what do you think would happen if we were to mix these two systems? The low temperature, low movement with the high temperature, high movement. Would all of them be low and slow, or would all of them be high and fast? Well, we know that heat always flows from an area of high thermal energy to an area of low thermal energy. So essentially, heat always flows from hot to cold. So for example, if you have a hot cup of coffee, the heat from that cup of coffee is going to move out. If you put it onto the table, the hot energy, the high energy is going to dissipate and move to the areas around it. Whereas when you have something that's cold, like a popsicle, it's eventually going to melt. Why? Because the heat from the room is warmer, and it's going to be moving in. It's going to go from the high heat, high thermal energy to the low thermal energy and allow those temperatures to eventually become kind of even with one another, right? That's kind of the purpose is heat wants to get to that high area, move to that low area, temperatures will eventually equalize. So when we think about that, when we think about that idea of these temperatures kind of equalizing, we think about, okay, well, heat's got to flow from one object to another, or one space to another, system to surroundings. We can actually take a look at this and use numbers to help us figure out what is going on. So we're going to do a heat exchange practice problem. So let's say that we have two beakers of water. We have one beaker of room temperature water, and a second beaker of warm or hot water. So let's say that beaker number one has a mass of 100 grams. Its specific heat is 4.18 because it's liquid water. And let's say that its initial temperature is about 22, which is kind of close to room temperature. And that the second beaker, this actually should say beaker number two, it says beaker number one, has a mass of 100 grams. It still has a specific heat of 4.18, right? And its initial temperature for this beaker is 62. So with our two beakers, the only difference is this one is cooler, this one is warmer. So what do you think would happen if we were to mix these two beakers, if we were to dump one into the other? Well, we know the individual Q, right? We could calculate the individual Q potentially for these two beakers, but we can only do that if we know what the final temperature would be. So if we look at these two substances, if one starts at 22 and one ends at 62, what do we know that the final temperature should be around? Well, if you have something that's cooler and something that's warmer and you mix the two of them, we're not going to have something that's hotter than 62 or cooler than 22. It's probably going to be a temperature somewhere in the middle. Can we say that it is smack dab in the middle? No, we can't do that. So what we have to do is we have to actually use a calculation to figure that out. But let's kind of backtrack and talk about something called the first law of thermodynamics. In thermodynamics, there's a lot of laws. We are only going to concentrate on the first one. And that states that whenever heat flows into or out of a system, the gain or loss of thermal energy equals the amount of heat transferred. So let's dive into that a little bit more. That basically states that the energy that goes in is equal to the energy that comes out. And what symbol do we normally use for energy? It's Q, right? So Q in is going to equal Q out. Well, we already know a couple of equations that use Q. So what this is we are going to be looking at Q of endo equaling Q of exo. Now, when people see this equation, normally they're like, wait a minute, there's a negative symbol. Well, we know that Q of endo is typically a positive number because energy is being absorbed, energy is increasing. And Q of exo is typically negative because we know that energy is being released. It is losing energy. Energy is negative. So then why wouldn't the negative be over here? Why is it with Q of endo? Well, remember, when something is endothermic, when energy is being absorbed, endothermics are always going to equal a positive value. And when something is exothermic, exothermics are going to equal a negative energy value. So that is why the negative is over here, because exo has to equal a negative and endo has to equal a positive. All right, so now that we have that straightened out, we know Q equals Q. Q of endo equals Q of exo. Q of the heat being absorbed equals Q of the heat being released. So if we go back to our two beakers, mass of 100, specific heat of 4.18 for both. This one starts at 22, this one starts at 62. Well, let's figure out which one is going to be which. Which one is going to be Q of endo and which one's going to be Q of exo? Well, this one, if we have cool water and warm water mixing, we're going to assume that this one that's cool is going to heat up. So beaker number 1 is going to be our Q of endo. And beaker number 2 starts at 62. It's going to get cooler because it's mixing with the cooler water. This part is going to be our Q of exo. So the energy lost by the warm water is the amount of energy gained by the room temperature water. So Q must equal Q. So if we need to figure out the final temperature, how do we set that up? Here's how we do it. We know that Q equals mc delta T. Q equals the mass times specific heat times the change in temperature. And since we know that the Q of the room temperature water, or the 22 degrees, is Q equals mc times delta T, final temperature minus initial temperature, and then Q of the hot water equals mc times the final temperature minus the initial temperature. And we know that Q of endo equals Q of exo. We can set them up equal to one another. So since negative Q of endo, or Q of the room temperature water, equals Q of the exo, or Q of the hot water, we can set up our equation like this because Q is equal to this. So we can drop the Q's because this is how you would calculate the Q's and substitute in mc delta T for those values. Now, we know what mc is for both. They're the same, 100 and 4.18. And we know that our initial temperature for our room temperature water was 22, and our initial water temperature for our hot water was 62. Then this is how we solve it. 100, mass of 100, specific heat of 4.18, final temperature minus 22, which was our initial temperature, is equal to the warm water, which is 100 grams, a specific heat of 4.18, final temperature, which we don't know, minus 62. So if we look on both sides of this equation, what are we trying to solve for? We're trying to solve for TF on both sides, which is the exact same variable. So if we very carefully solve for TF, what are we going to get? So take a moment, pause the video, take a moment right now, and see if you can try to solve for TF on your own. Did you do it? All right, so if we've solved for TF very carefully with multiplying, dividing, subtracting, all of that, we should get a final temperature of 42 degrees Celsius. Now, it just so happens that this number is smack dab in the middle of these two values. But is it always going to be like that? Not necessarily. So that is how we can figure out the final temperature when we mix two substances at, well, in this case, the same substance at two different temperatures.